day 27 of 50 days of tutelage, and in today's class I'll be teaching you about oxidation and reduction, otherwise also known as redox. RED for reduction and OX for oxidation. I'm going to be giving you the definition of oxidation and reduction. I'm going to be using some old definition and some new definitions as well. So in chemical reactions, a lot of things usually go on, and one of them is oxidation and reduction. Fine, there are some chemical reactions that don't involve that are not redox reaction, because if it's a redox reaction, there will be both oxidation and reduction present in it. So I'm going to be showing you those ones that involve a redox reaction and how you can identify what is going on with one and what is going on with the other. So the first definition I'm going to be giving you, two of them actually, they are the two old definitions, and I'm going to be giving you the two of them together simultaneously, is from just the way the name sounds. Whenever you say oxidation, oxidation is simply the addition of oxygen. So something that does not have oxygen before, or something that probably does not have as much oxygen before, you add oxygen to it, then you say that thing has become oxidized. Then if you remove oxygen as well, so removal of oxygen, then this is called reduction. So addition of oxygen is oxidation, removal of oxygen is reduction. Then the one I'm going to define simultaneously with it is the use of hydrogen. In the case of hydrogen, it's actually kind of vice versa. It's what I mean vice versa, I mean like it's the reverse case. So when you add hydrogen, when hydrogen is added, you have reduction. And then when you remove hydrogen, you have what? You have oxidation. So let me use this thing to explain. You all familiar with the reaction between hydrogen gas and oxygen gas to give water, H2O. So first thing you notice is that this hydrogen gas is separate here. It does not have any oxygen with it. It's alone. And therefore, it has changed now from this place and it has now become H2O. So the hydrogen now has oxygen with it. Therefore, it has moved from the state of not having oxygen to a state of having oxygen. So the process of hydrogen gas becoming H2O is going to be oxidation process. But the same thing is not only this hydrogen gas that formed this, oxygen is also one of them. So the process through which this oxygen moved from this place to become this. Now, in this case now, what has been added to oxygen? Hydrogen has been added to oxygen in this situation. So therefore, it has undergone reduction. Like I said, addition of hydrogen is what? Reduction. So this equation now is a redox reaction because it involves both oxidation and reduction. So I've been able to define the two things in terms of oxygen and in terms of hydrogen. However, these are old definitions. We have better definitions that we use. And then the first one is the loss or gain of electron. Loss or gain of electron. So what happened is that if you are considering a particular atom, either in a compound or standalone or in a molecule, if you're considering an atom and then the atom is transitioning from one place to another, from the reactant side to the product side, if the atom actually loses electron, then you say it has become what? It has become oxidized if it loses electron. So loss of electron is oxidation and gain of electron is reduction. Which leads me to the next definition. I'm going to explain this better, but I have to always define them simultaneously so that I will explain them together and you understand. So it leads me to the concept of what we call oxidation state. Something called oxidation state of atom in a compound or in a molecule. If you don't know the oxidation state, there's no way you'll be able to tell whether there's a loss or there's a gain of electron. So you need to know the oxidation state. Oxidation state varies. It can be negative, it can be zero, and it can be positive. So therefore, if you transition from, let's say, negative to positive, you have increased your oxidation state. If you have transitioning from zero to positive, you have increased as well. But if you're going anything backward, you are reducing your oxidation state. So that is why another definition that we use to define oxidation and reduction is that if you have increase in your oxidation state, that is also oxidation. Increase in oxidation state, that is also oxidation. And decrease in your oxidation state, that is reduction. Now you see how all of these blend. By the way, you need your notes. Take your notes and make sure you are actually jotting things down. Also, if you're not subscribed to the channel, this is the right moment for you to subscribe. Just hit the subscribe button and like the video as well. So let's continue. So oxidation, I've said, it is the loss of electron, and reduction is the gain of electron. But also in terms of oxidation state, it is increase in oxidation state is oxidation, and decrease in oxidation state is what? Reduction. And what is this oxidation state? I'm still going to explain everything that we have here. So just make sure that you are following. Yes, everything that is here, I'm going to explain them. I'm just building something up. So what is oxidation state? Oxidation state is like the apparent charge of an atom in a compound. Apparent charge of an atom in a compound. Now, the first rule that you must know is that if we have neutral elements, for neutral elements, their oxidation state is always going to be zero. For neutral elements, their oxidation state is going to be zero. And neutral element, this hydrogen gas now is existing in its neutral state as a diatomic element, and oxygen gas is also existing as a what? Diatomic element. So therefore, their oxidation states, they are both what? In their zero oxidation state. So anytime you pick any elements and they are in their natural state, they are not combining with anything, they are not forming a compound, neutral elements like that, they have their oxidation state to be zero. So now, how do you now calculate the oxidation state when they are in a compound? I'm going to give you an example. For example, if you have, let's say, K2SO4. Now, K2SO4 now is a compound. In fact, we are going to name this thing later, but I'm not naming them now. I'm talking about oxidation state first. Now, usually, we know the oxidation state of oxygen. It's a common thing. And we know that of potassium. Potassium is K plus in the activity series, and oxygen is O2 minus. If you don't know how to do this, we've done this thing in our previous classes with how we know the oxidation, how we know the ions, the valency. Yes, we've discussed about valency, electrovalency, covalency, and all of those things. So you want to check out the previous videos to understand this. So potassium is K plus and oxygen is O2 minus. So in that situation, sulfur is the one that will have an undetermined oxidation state here. So therefore, we're going to determine the oxidation state of sulfur in this situation. So let's go now. We have K plus and we have 2 of it. So K plus means plus 1. So we have 2 of it. That's going to be 2 multiplied by plus 1. Then sulfur, let me just represent it with S. Plus oxygen, how many do we have here? 4 of oxygen. So we have 4. And then here we have 2 minus, which is going to be negative 2. So this is negative 2. Now, neutral elements and also neutral compounds as well, they always have their oxidation state to be equal to 0. So this K2SO4, in total, the total oxidation state is going to be equal to 0 because it is not charged. It's only the individual atoms there that are charged, that are forming ions. But in the entire compound is not charged. So therefore, the net charge will be equal to 0. So therefore, you have 2 times positive 1, that's 2, plus S. 4 times negative 2, that's negative 8, equals 0. And if you solve this very well, S is going to be what? Plus 6. So therefore, the oxidation state of sulfur in this place is plus 6. So you take note of that. So going back to what I gave earlier, so hydrogen, you have oxygen. Of course, we know that hydrogen is H plus and oxygen is what? O2 minus. So let's see what has happened here. You've noticed that hydrogen has gone from the state of 0 oxidation state to the state of what? To the state of plus 1 oxidation state. That's an increase in oxidation state. So it establishes that this is actually an oxidation process. Then the second one, oxygen has gone from the state of 0 to negative 2. Therefore, it established that it has gone through what? Reduction. So how do we now know which one has gained electron, which one is losing electron? From what I told you earlier in our previous classes, I told you that when bonding wants to take place, especially if it is the case of ionic bonding, for instance, so let's say you have this now, let's say you have sodium reacting with chlorine, and this gives NaCl. Of course, you should balance the equation. So put a 2 here and put a 2 here. The equation is balanced now, but that's not really what I'm interested in. In this case, the oxidation state of sodium is 0, and for chlorine here is also 0 because they are in their neutral form now. But in this situation, let's see which one is oxidation and which one is reduction. Let's use the gain and loss of electron. I told you that when I was teaching about bonding, I said whenever we need a perfect donor and a perfect receiver, and they do this by transferring their valence electron. So if you were in that class, you know that sodium belongs to the perfect donor. Sodium will be the one to give out electron, and then chlorine will be the one to receive electron in this situation. So therefore, sodium will be the one that will go through oxidation because it is the one giving out the electron, while chlorine will be the one to go through reduction because it is the one receiving the electron. So I've been able to define, I'll give you all the definitions that has to do with redox reaction. So you should know that, and then you can go ahead and use the other thing that I said earlier. There's one loose one that I will try to use, like addition of electronegative elements and addition of electropositive elements, but they all fall under what I've already explained. And so that's like the basic introduction to redox reaction. So I've also taught you oxidation states and all of those things. So you should be able to identify oxidation states of different substances. Now, before I proceed, I mentioned something here earlier about determining the oxidation state of a particular atom in a given compound. So I'm going to give one example, and I'm going to show you how we use that to determine the IUPAC name of substances. How we use that to determine the IUPAC name of some substances. I'm looking for a perfect example to use, so I'm going to use one of the common ones. I'm going to use K2Cr2O7. So we want to name this thing now, and I want to show you how to name it. Obviously, you know that oxygen, the common one, potassium, also the common one. So therefore, I need to determine for this chromium. So let's go. We can say K is K plus, so that will be 2 times plus 1, plus 2 times, this is the unknown one, so let's make it 2x, because we have 2 atoms of it here, then plus 7 times negative 2, that is for oxygen. Everything here is going to be equal to 0. So we have 2 plus 2x, 7 times negative 2, that's negative 14, and that will be 0. And this implies that 2x, 2 minus 14, that is going to be negative 12, equals 0. And that implies that x is going to be equal to 6 here, plus 6. So therefore, let us now name this guy. So the way you do it is that you name the cation first, which is, in this case, potassium. So you have potassium, then you go to the oxygen part, then you say, how many oxygen do we have here? 7. 7 is hepta. So you have heptaoxo, potassium heptaoxo. Then you now go to this guy. First of all, how many atoms do you have there? 2 atoms. So you have heptaoxo dichromate. Now, after saying that dichromate, what is the oxidation state? 6. Heptaoxo dichromate 6. So the name of this guy is potassium heptaoxo dichromate 6. Now, I want to show you something. Actually, Cr2O7 is a radical. So what if we want to name it like this and we want to calculate the oxidation state of chromium here? So that is going to be, we have, so let's say 2x plus 7 times negative 2. As you can see, 2x, then 7 times negative 2. I'm not saying negative 2 because of this, because of oxygen that we know. But now, since this is charged, it is not a neutral compound. So therefore, the net charge of everything here is going to be equal to the charge that we have here. And that's going to be negative 2. So therefore, you have 2x plus 7 times negative 2, that's negative 14, equals negative 2. So what do we have here? We have 2x equals negative 2, then you have plus 14, and 2x will be equals to negative 2 plus 14 is 12. When you solve for x in this place, it's 6. So you can see that this is actually still 6. So therefore, the name of this one is just this. You have the heptaoxodichromate 6. But when you bond it with a cation like potassium now, you have potassium heptaoxodichromate 6. And that's how you use the concept of oxidation state to name compounds like that. One that is very, very important is the case of when you have transition metals. Like for instance, if you have FeSO4, actually this FeSO4 is it has iron has variable oxidation state because it is a transition metal. So because it can also be like this, it can be Fe2 then SO4 3. In this case, the oxidation state of iron here is plus 2. The oxidation state of iron here is plus 3. In chemical bonding, I already explained how they bond. In this place, you have Fe2 plus and you have SO4 2 minus. In this place, you have Fe3 plus and you have SO4 2 minus. So what happens is that they exchange that power. They exchange that power to form their base. In this situation, 2, 2. So therefore, there's no need of writing any of them. They just cancel out. So FeSO4. In this case, 2 comes down to Fe and 3 goes down to SO4. I've already explained this earlier. So how do you name this now? You name it so that you give the oxidation state of iron first that you're using here. So you have iron 2. Then you now name this other guy. Tetra is 4. Tetraoxosulfate. So you can also calculate this now. This will be plus 2 plus S plus 4 times negative 2. Everything will be equal to 0. So you have 4 times negative 2 is negative 8. So negative 8 plus 2 is negative 6. So S is going to be plus 6 now. So that will be iron 2 tetraoxosulfate 6. Iron 2 tetraoxosulfate 6. And that's that about that. So the next thing I want to teach you is how to balance redox reaction. How to balance redox reaction. Now, there are two medium that are media that I'm going to be using. We have the acidic and we have the basic media. For the acidic medium, I want you to just check, use the link that is popping up right now. You can check, I've made a detailed video about that. And once you know how to balance in acidic medium, then how to balance in basic medium is also going to be very, very easy as well. So I'm going to use this example to show you how to balance in basic medium. So let me just go to this next page. So if you have, let's say, the reaction between silver plus zinc to give this plus zinc. So let's say this is the reaction that we are dealing with here. Of course, the reason why we are writing zinc in the oxidation with zinc 2 plus is because it is actually bonding with something and we are not really like, we're not interested in writing it here. It could be oxygen, it could be some other things, but we're not interested. We just want to balance this chemical equation. So let's see how we go about that. So the first thing is that you have to separate them into the half redox reactions. That is, whether it is oxidation or it is what? Reduction. So you want to separate them. First of all, this guy is in its 0 oxidation state. This guy is in the plus 2 oxidation state. And this guy, because it is neutral, it is not carrying any charge. So it will be in the 0 oxidation state. This one is in plus 2. So automatically you know that zinc is being what? Is being reduced. So zinc is being reduced. So therefore, you separate it into the reduction and the oxidation. So we call them the half equations. So we have reduction, that's from Zn2 plus to Zn. And then obviously the oxidation will be from Ag to what? Ag2O. And as you can see there, you can see that there is addition. Let me write that properly. Ag2O. You can see that there is addition of oxygen. So that perfectly follows the definition I gave you earlier. So how do we do this now? So the first thing you need to do is that you pick them one after the other. You can pick this one first. You balance them atomically. Then you balance them charge-wise. So for this first case now, I have Zn2 plus, and I'm going to balance it atomically now. So to balance it atomically, it's already balanced atomically. I have Zn2 plus here, I have Zn here, 1 atom of zinc, 1 atom of zinc. But charge-wise, it is not balanced. It is balanced. This one has a plus 2, and this one has 0, no charge here. We have to balance it. So, and what do we balance with? We always balance with electrons. In this place, you have 0 on the right, you have plus 2 on the left. What's the difference in their charge? That would be 2 minus 0, that would be plus 2. So therefore, you need 2 electrons to do this balancing. And you always add the electron to the side that has the highest power. So in this situation, you're going to add 2 electrons to this side like that. So you have plus 2 electrons. I believe that makes sense. Now, the next thing we want to do is that we want to balance the oxidation part. Now, this is where the work actually is going to be. Let's balance atomically first. In this place, you can see that we have Ag here, we have Ag here. But in this place, how many of Ag do we have? We have 2 of it, and you have only 1 of it here. So therefore, to balance it, we can put a 2 behind this. So Ag is balanced, Ag is balanced. You can see that I did not bother about oxygen. That's because oxygen is on the right, but it is not on the left. So how do we balance oxygen? The first thing you do is that to balance oxygen, we always use water to balance oxygen. So ask yourself, how many oxygen do we have here to balance? Only 1 of it. So therefore, you have 1 mole of water, you add it to the other side. So you have 2Ag plus H2O. Then, in that case, you have Ag2O like that. So you are getting there. Now, something else has been introduced, which is what? Hydrogen, because hydrogen was not here in the first place. To balance hydrogen, what do we use? We use proton. That is our H plus. So how many hydrogen do we have here? 2 of them. So therefore, we introduce what? We introduce 2H plus in this place. Now that we are done with that, all the atoms are balanced. Ag here, silver, 2, silver here, 2. Oxygen here, 1, oxygen here, 1. Hydrogen here, 2, hydrogen here, 2 as well. The next thing that is not balanced is charge. The total net charge we have here is 0. And the total net charge here we have here is what? Plus 2, because you have 2 atoms here and you have plus 1. So that will be plus 2. So therefore, to balance this, we need to actually add electron to the side that has the higher charge here. In this case, you have plus 2 electrons. I've already explained that earlier. One thing you should watch out is that for your reduction and oxidation, the electrons will always be on opposite sides. If you have your electron on the same side for your reduction and oxidation, then you probably have done something wrong. So you need to watch that very well. You need to watch that very, very, very well. So now that we have done with this, the next thing we want to do is that, now we're still going to do some other things because I'm balancing in basic medium. I'm balancing in basic medium, but I'm trying to do acidic medium first. So that's why you need to actually watch that video to understand this properly. Now, you're going to add the 2 equations together. And to add the 2 equations together, whenever there is a version of something on the left and the same version on the right, what you do is that you always give the version with the higher one. That will be the one that will take the whole thing. I'm going to explain what I'm saying now. For instance, you have 2 electrons here. You have 2 electrons here. They are on different sides, so therefore they cancel out. In this place, you have zinc, Zn2 plus. Now, of course, on the right hand side, you have zinc. They are not the same thing. Then you have plus. In this place, you have 2 mole of silver. Then you have plus H2O. This gives, you have zinc. Then you have plus Ag2O plus 2H plus. Now, what I've done now is that I've not balanced it in basic medium yet. I'm doing the preliminary first. To now do the balancing in basic medium thing, that is, we're not using hydrogen ion, we want to use OH minus. So instead of hydrogen ion, we want to use what? We want to use OH minus. So to do that, what we have to do is that look at the number of hydrogen ion that you have here and use OH minus to balance it. So in this place, you can see that how many hydrogen ion do we have here? We have 2 of it here. So since we have 2 of it here, I'm going to balance it and turn it to plus 2OH minus. I'm going to do that same thing here, plus 2OH minus. Whatever you're doing for one side, you need to do it for the other side as well. So when you write this now, this is going to be zinc 2 plus 2Ag plus H2O plus 2OH minus to give zinc plus Ag2O plus, now H plus and OH minus, they will turn to water. And how many of them do you have? 2 to each. So that means that you have 2 molecules of water being formed here. we are almost done. We have gotten rid of the H plus there. We now have OH minus, showing that it is in the basic medium. So the next thing we want to do is that there is water here, there is water here. Water has to remain on one side, and it will remain on the side with the higher number. But we have one of it here, we have two of it here. So 2 minus 1 is 1. That one will be on the right hand side with the one with the higher side. So therefore, you have zinc Zn2 plus silver plus OH minus plus zinc plus Ag2O. Finally, you have plus 1 mole of water. And with this, you have been able to balance this particular reaction in the basic medium. So you can confirm atom-wise and also charge-wise. So you can see that from the left, we have how many zinc do we have here? We have 1 zinc. We have 1 zinc. And then how many zinc do we have here? 1 zinc. How many silver do we have here? 2. How many silver do we have here? 2. How many oxygen do we have here? 2 oxygen. How many oxygen do we have here? 1, 2. How many hydrogen do we have here? 2. How many hydrogen do we have here? 2. What's the total charge that we have here? That is a plus 2 and a minus 2. That's what? 0. And all of these, none of them is charged, so we have 0. So therefore, this is balanced. And that's it for oxidation and reduction. Make sure you like and subscribe to the channel. I'll see you in the next one.